Hi, now let's discuss about nuclear medicine imaging, especially PET. So, principle of positron emission tomography. So that is using gamma photons passing through the body and can be measured by a gamma detecting device that encircles the subject's body, or it could be head. And these PET scanner will be a size of similar to our human, because our human body has to be inside a bore. And then the gamma photons, which is generated, will have exactly the same, the opposite direction, and can be detected by these scintillating detectors. And so we want to detect the tiny time difference between, so that we can have, if it's exactly the same, it's in the middle. If it's on the a little bit side, the detection time will be shorter, longer here, shorter here, and longer here. And that tiny time difference gives on this line where were the location of the original emission. So that is about actually a few nanosecond time difference. And remember, we are using eventually AD converter and electronics to find out the difference. So electronics can measure as short as a nanosecond, and it happens to be pretty good for using electronics to use it for PET detection. So I'll give you just a rough ballpark figure here. The delta T time difference will be the distance divided the velocity. And in this case, gamma photons pass through the space almost in speed of the light. And the distance will be on the order of a meter scale at the largest. So that if you quickly calculate 1 meter divided by 3 times 10 to the 8 meter per second, which is speed of light, and you result in a few nanoseconds, which is allowed by our fast electronics to detect. So gamma photon or gamma radiation, or we call gamma ray, is ionizing radiation, which is produced from gamma decay, and it has wavelength of less than 10 picometer, and in terms of energy, a few hundred kilo electron volts. So I want to discuss about the imaging method of PET. So first, detector side. So PET uses a detector using the PMT photomultiplier tube, which detects very fast and sensitively the photons coming up. However, it starts with the nuclear medicine, starts with a gamma ray. So we need to have converting gamma ray into a photons. That we call scintillator crystals. So this 1 unit of PMT and scintillator is a detector block. And for the principle of PET, we do need a circling many number of these detector blocks. So you can see here, not only one rim, but it could be multiple rims to detect like 3-dimensional structure. And that you can imagine it costs a lot, because there are many PMTs, which is very costly. And here is the diagram of how this PMT works. And we already discussed high energy photons such as gamma rays in. And in front, there's a scintillator crystal, which will convert this high energy gamma ray into a photon or fluorescence. And that photons will hit a photocathode, which based on photoelectric effect, it will generate primary electron, and that could be accelerated to dynodes and diodes for secondary emission of electron. So huge amplification of electrons, such as 10 to the 5th to 10 to the 8th times of electron generate a current, and you can detect it. And that is the photomultiplier tube with this scintillator. So that's how the detector part of the positron emission tomography, how we image with PET or positron emission tomography. We are using very short-lived radioisotope that emits particles are called, yes, as the name says, positrons. Okay, so so that looks like this. So this is a from the radioisotope of positrons, which is denoted as a E plus because the charge is the same as electron, but it's positive, and that comes out and it hits inside the tissue with the first electron to annihilate. Then that will generate 2 photons with that energy with the 2 gamma rays, which is opposite direction. And that gamma ray can be detected here and here, and we need to compare the coincidence time difference so that we can determine the location of this annihilation happens. So by the way, we can see the start of this positron starting out and versus by the time it hits this electron for annihilation, there's usually about a millimeter difference. So that's why in PET, even if we do a very good job, the resolution cannot be better than a millimeter. So typically that then makes this PET limits the resolution of the PET. And the positron is an antimatter counterpart of an electron. And when in contact with an electron and annihilation occurs, then that results in a pair of gamma photons in opposite direction. The reason is to preserving momentum. And for this very short-lived radioisotope for PET, we are using, we need a cyclotron, which is a type of particle accelerator to produce short-lived compounds. For example, C11, carbon, nitrogen 13, and F18. And these have pretty relatively short lives. So that's why PET is a device which also needs, at least in the same city or in a near place, a cyclotron. So what is cyclotron? This is just for reference to give you an idea where the name comes from. And you will see it's an apparatus which charges the atom and subatomic particles are accelerated by alternating electric field and it in a circular path. That's why it's called cyclotron. And in nuclear medicine, over the world, in many big hospitals which has a nuclear medicine department, will have likely to have cyclotron to produce this radionuclide. So this is a diagram that inside here, charged particle starts, and these 2 electrodes will alternate generating electric field to accelerate the particle from here to here. It gains its kinetic energy. That's why it gets a bigger radius. And then eventually it is accelerate and fast enough to target and producing radionuclides. So thin aluminum foil window. All right, and for this we need a huge magnetic coil up and down.